ಇದು ಮಾಹಿತಿ ಖಜಾನೆ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ
ಮಾಹಿತಿ ಖಜಾನೆ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿಗೆ ನನ್ನೆಲ್ಲ ಸಂಯುಕ್ತರಿಗೂ ಆತ್ಮೀಯವಾದ ಸ್ವಾಗತ. ಇಂದು ನಾವು ಮತ್ತೊಂದು ಉಪಯುಕ್ತ ಮಾಹಿತಿಯೊಂದಿಗೆ ಬಂದಿದ್ದೇವೆ. ಈ ವಿಡಿಯೋ ನಿಮಗೇನಾದರೂ ಇಷ್ಟವಾದಲ್ಲಿ ಲೈಕ್, ಶೇರ್, ಕಾಮೆಂಟ್ ಮಾಡಿ ಹಾಗೂ ಇನ್ನೂ ಹೆಚ್ಚು ಉಪಯುಕ್ತ ಮಾಹಿತಿಯನ್ನು ನಮ್ಮ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿಯಿಂದ ಏನಾದರೂ ನಿರೀಕ್ಷಿಸುತ್ತಿದ್ದೀರಾ? ನಿರೀಕ್ಷಿಸಿದಲ್ಲಿ ಬೆಲ್ ಐಕಾನ್ ಅನ್ನು ಕ್ಲಿಕ್ ಮಾಡುವುದರ ಮೂಲಕ ಸಬ್ಸ್ಕ್ರೈಬ್ ಆಗಿ.
Each of the 248 channels is additionally separated in time via a GSM TDMA frame, i.e., each 200 kHz carrier is subdivided into frames that are repeated continuously. The duration of a frame is 615 milliseconds. A frame is again subdivided into 8 GSM time slots, where each slot represents a physical TDM channel and lasts for 577 us. Each TDM channel occupies the 200 kHz carrier for 577 us every 615 milliseconds. Data is transmitted in small portions, called bursts. The following figure shows a so-called normal burst as used for data transmission inside a time slot. As shown, the burst is only 5 microseconds long and contains 148 bits. The remaining 5 microseconds are used as guard space to avoid overlapping with other bursts due to different path delays and to give the transmitter time to turn on and off. The first and last 3 bits of a normal burst, tail, are all set to 0 and can be used to enhance the receiver performance. The training sequence in the middle of a slot is used to adapt the parameters of the receiver to the current path propagation characteristics and to select the strongest signal in case of multipath propagation. A flag S indicates whether the data field contains user or network control data. Apart from the normal burst, ETSI 1993A defines 4 more bursts for data transmission. A frequency correction burst allows the MS to correct the local oscillator to avoid interference with neighboring channels. A synchronization burst with an extended training sequence synchronizes the MS with the BTS in time. An access burst is used for the initial connection set up between MS and BTS. And finally, a dummy burst is used if no data is available for a slot. Logical channels and frame hierarchy. 2 types of channels, namely physical channels and logical channels, are present. Physical channel defined by specifying both a carrier frequency and a TDMA time slot number. Logical channels are multiplexed into the physical channels. Each logic channel performs a specific task. Consequently, the data of a logical channel is transmitted in the corresponding time slots of the physical channel. During this process, logical channels can occupy a part of the physical channel or even the entire channel. Each of the frequency carriers is divided into frames of 8 time slots of approximately 577 microseconds, 15/26 microsecond, duration, with 156.25 bits per time slot. The duration of a TDMA frame is 615 milliseconds, 577 microseconds x 8 is equal to 615 milliseconds. The bits per time slot and frame duration yield a gross bit rate of about 271 kbps per TDMA frame. TDMA frames are grouped into 2 types of multiframes. Medium black circle 26-frame multiframe 615 milliseconds x 26 is equal to 120 ms, comprising of 26 TDMA frames. This multiframe is used to carry traffic channels and their associated control channels. 51-frame multiframe 615 milliseconds x 51 235, 4 milliseconds, comprising 51 TDMA frames. This multiframe is exclusively used for control channels. The multiframe structure is further multiplexed into a single superframe of duration of 6.12 seconds. This means a superframe consists of 51 multiframes of 26 frames, 26 multiframes of 51 frames. The last multiplexing level of the frame hierarchy, consisting of 2048 superframes, 271.5648 TDMA frames, is a hyperframe. This long time period is needed to support the GSM data encryption mechanisms. The frame hierarchy is shown below. Hyperframe 2048 superframes, periodicity equals 3h 28 minutes, and 53 seconds 760 milliseconds 0. 1 2 3 4 5 superframe 51 by 26 multiframe, or 26 times 51 multiframe periodicity equals 6s 120 milliseconds 0. 1 2 3 4 0. 1 2 26 multiframe 26 TDMA frames periodicity equals 120 milliseconds, 4 TCHs, 0 1 2 0. 2044 2045 2046 2047 47 48 49 50 and LT equals 26 multiframes 24 25 and LT equals 51 multiframes 51 multiframe 51 TDMA frames periodicity equals 235. 38 milliseconds, 4 signaling, 24 25 0. 1 2. TDMA frame 8 TS's periodicity equals 4. 615 milliseconds, 1 2 3 4 5 6 GSM, frame hierarchy 7. 48 49 50. There are two different types of logical channel within the GSM system: traffic channels, TCHs, control channels, CCHs. Traffic channels. Traffic channels carry user information, such as encoded speech or user data. Traffic channels are defined by using a 26-frame multiframe. Two general forms are defined: I2. Full-rate traffic channels, TCHF, at a gross bit rate of 22. 8 kbps, 456 bits for 20 ms, half-rate traffic channels, TCHH, at a gross bit rate of 11. 4 kbps. Uplink and downlink are separated by 3 slots, bursts, in the 26 multiframe structure. This simplifies the duplexing function in mobile terminals design, as mobiles will not need to transmit and receive at the same time. The 26-frame multiframe structure, shown below, multiplexes two types of logical channels: a TCH and a slow associated control channel, SACCH. However, if required, a fast associated control channel, FACCH, can steal TCH in order to transmit control information at a higher bit rate. This is usually the case during the handover process. In total, 24 TCH, F, are transmitted, and 1 SACCH. Half rate 11. 4 kbps speech TCH, traffic, full rate 22. 8 kbps minus 2. 4 kbps data minus 4. 8 kbps 9. 6 kbps BCH FCCH, frequency correction, SCH, synchronization, PCH, paging, CCCH RACH, random access, CCH, control, AGCH, access grant, dedicated SDCCH, standalone, SACCH, slow associated, FACCH, fast associated, control channels. Control channels carry system signaling and synchronization data for control procedures such as location registration, mobile station synchronization, paging, random access, etc. between base station and mobile station. 3 categories of control channel are defined: broadcast, common and dedicated. Control channels are multiplexed into the 51-frame multiframe. 12. Broadcast control channel, BCCH. A BTS uses this channel to signal information to all MSS within a cell. Information transmitted in this channel is, e.g., the cell identifier, options available within this cell, frequency hopping, and frequencies available inside the cell and in neighboring cells. The BTS sends information for frequency correction via the frequency correction channel, FCCH, and information about time synchronization via the synchronization channel, SCH, where both channels are subchannels of the BCCH. Common Control Channel, CCCH. All information regarding connection set up between MS and BS is exchanged via the CCCH. For calls toward an MS, the BTS uses the paging channel, PCH, for paging the appropriate MS. If an MS wants to set up a call, it uses the random access channel, RACH, to send data to the BTS. The RACH implements multiple access. All MSS within a cell may access this channel, using slotted aloha. This is where a collision may occur with other MSS in a GSM system. The BTS uses the Access Grant Channel, AGCH, to signal an MS that it can use a TCH or SDCCH for further connection setup. Dedicated Control Channel, DCCH. While the previous channels have all been unidirectional, the following channels are bidirectional. As long as an MS has not established a TCH with the BTS, it uses the standalone Dedicated Control Channel, SDCCH, with a low data rate, 782-bit S, for signaling. This can comprise authentication, registration, or other data needed for setting up a TCH. Each TCH and SDCCH has a slow associated Dedicated Control Channel, SACCH, associated with it, which is used to exchange system information, such as the channel quality and signal power level. Finally, if more signaling information needs to be transmitted and a TCH already exists, GSM uses a fast associated Dedicated Control Channel, FACCH. The FACCH uses the time slots, which are otherwise used by the TCH. This is necessary in the case of handovers where BTS and MS have to exchange larger amounts of data in less time. GSM protocols. The signaling protocol in GSM is structured into 3 general layers depending on the interface, as shown below. Layer 1 is the physical layer that handles all radio-specific functions. This includes the creation of bursts according to the 5 different formats, multiplexing of bursts into a TDMA frame, synchronization with the BTS, detection of idle channels, and measurement of the channel quality on the downlink. The physical layer, uses GMSK for digital modulation and performs encryption or decryption of data, i.e., encryption is not performed end-to-end, but only between MS and BSS over the air interface. 13. MSBTS, BSC Master of Science CM mm BSSAP, R LAPT R BSSAP, R BTSM, BTSM, S87SS, 7 LAPT Radio PCM 16/64 kbit S protocol architecture, for signaling 64 kbit S2, 048 Mbit. The main tasks of the physical layer comprise channel coding and error detection or correction, which is directly combined with the coding mechanisms. Channel coding makes extensive use of different forward error correction, FEC, schemes. Signaling between entities in a GSM network requires higher layers. For this purpose, the LAPDM protocol has been defined at the interface for Layer 2. LAPDM has been derived from Link Access Procedure for the D-channel LAPT in ISDN systems, which is a version of HDLC. LAPDM is a lightweight LAPT because it does not need synchronization flags or checksumming for error detection. LAPDM offers reliable data transfer over connections, resequencing of data frames, and flow control. The network layer in GSM, Layer 3, comprises several sublayers. The lowest sublayer is the Radio Resource Management, RR. Only a part of this layer, RR, is implemented in the BTS, the remainder is situated in the BSC. The functions of RR are supported by the BSC via the BTS Management, BTSM. The main tasks of RR are setup, maintenance, and release of radio channels. Mobility management, millimeter, contains functions for registration, authentication, identification, location updating, and the provision of a temporary mobile subscriber identity, TMSI. Finally, the call management, CM, layer contains three entities: call control, CC, short message service, SMS, and supplementary service, SS. SMS allows for message transfer using the control channels SDCCH and SACCH, while SS offers the services like user identification, call redirection, or forwarding of ongoing calls. CC provides a point-to-point connection between two terminals and is used by higher layers for call establishment, call clearing and change of call parameters. This layer also provides functions to send in-band tones, called dual tone multiple frequency, DTMF, over the GSM network. These tones are used, e.g., for the remote control of answering machines, or the entry of pins in electronic banking, and are also used for dialing in traditional analog telephone systems. Additional protocols are used at the A and A interfaces. Data transmission at the physical layer typically uses pulse code modulation, PCM, systems. LAPT is used for layer 2 at ABI, BTSM for BTS management. Signaling system number 7, SS7, is used for signaling between an Master of Science and a BSc. This protocol also transfers all management information between MSCs, HLR, VLRS, AUC, EIR, and OMC. And Master of Science can also control a BSS via a BSS application part, BSSAP. Localization and calling. The fundamental feature of the GSM system is the automatic, worldwide localization of users for which the system performs periodic location updates. The HLR always contains information about the current location, and the VLR currently responsible for the MS informs the HLR about the location changes. Changing VLRs with uninterrupted availability is called roaming. Roaming can take place within a network of one provider, between two providers in a country, and also between different providers in different countries. To locate and address an MS, several numbers are needed. Mobile Station International ISDN number, MSISDN. The only important number for a user of GSM is the phone number. This number consists of the country code, CC, the national destination code, NDC, and the subscriber number, SN. International Mobile Subscriber Identity, IMSI. GSM uses the IMSI for internal unique identification of a subscriber. IMSI consists of a mobile country code, MCC, the mobile network code, MNC, and finally the mobile subscriber identification number, MSIN. Temporary Mobile Subscriber Identity, TMSI, to hide the IMSI, which would give away the exact identity of the user signaling over the air interface. GSM uses the 4-byte TMSI for local subscriber identification. Mobile Station Roaming Number, MSIN. Another temporary address that hides the identity and location of a subscriber is MSIN. The VLR generates this address on request from the Master of Science, and the address is also stored in the HLR. MSIN contains the current visitor country code, VCC, the visitor national destination code, VNDC, the identification of the current Master of Science together with the subscriber number. The MSIN helps the HLR to find a subscriber for an incoming call. 15. For a mobile terminated call, MTC, the following figure shows the different steps that take place. Calling station HLR VLR 89361415 PSTN GMSC Master of Science 1. 210 10 13 10 16 BSS, BSS, 11 12 17 MS BSS, Mobile Terminated Call, MTC, Step 1, user dials the phone number of a GSM subscriber. Step 2, the fixed network, PSTN, identifies the number belongs to a user in GSM network, and forwards the call setup to the Gateway Master of Science, GMSC. Step 3, The GMSC identifies the HLR for the subscriber and signals the call setup to HLR. Step 4. The HLR checks for number existence and its subscribed services and requests an MSIN from the current VLR. Step 5. VLR sends the MSIN to HLR. Step 6. Upon receiving MSIN, the HLR determines the Master of Science responsible for MS and forwards the information to the GMSC. Step 7. The GMSC can now forward the call setup request to the Master of Science indicated. Step 8. The Master of Science requests the VLR for the current status of the MS. Step 9. VLR sends the requested information. Step 10. If MS is available, the Master of Science initiates paging in all cells it is responsible for. Step 11. The BTSS of all BSSS transmit the paging signal to the MS. Step 12. Step 13. If MS answers, VLR performs security checks. Step 15. Till Step 17. Then the VLR signals to the Master of Science to set up a connection to the MS-16. For a mobile originated call, MOC, the following steps take place. VLR 3. 5 PSTN, GMSC Master of Science 8. 2-1. MSBSS 10. Step 1. The MS transmits a request for a new connection. Step 2. The BSS forwards this request to the Master of Science. Step 3. Step 4. The Master of Science then checks if this user is allowed to set up a call with the requested and checks the availability of resources through the GSM network and into the PSTN. If all resources are available, the Master of Science sets up a connection between the MS and the fixed network. In addition to the steps mentioned above, other messages are exchanged between an MS and BTS during connection setup in either direction. MSBTS, paging request channel, request immediate assignment, paging response service, request authentication, rec authentication, resp authentication, resp ciphering, command ciphering, complete setup, call confirmed, assignment, complete assignment, complete alerting, connect, act, data exchange. Message flow for MTC and MOC 17. Handover cellular systems require handover procedures, as single cells do not cover the whole service area. However, a handover should not cause a cutoff, also called call drop. GSM aims at maximum handover duration of 60 milliseconds. There are two basic reasons for a handover. 1. The mobile station moves out of the range of a BTS, decreasing the received signal level, increasing the error rate, thereby diminishing the quality of the radio link. 2. Handover may be due to load balancing, when in Master of Science a BSC decides the traffic is too high in one cell and shifts some MS to other cells with a lower load. The four possible handover scenarios of GSM are shown below: MS, BTS, BSC, Master of Science, intracell handover. Within a cell, narrowband interference could make transmission at a certain frequency impossible. The BSC could then decide to change the carrier frequency. Scenario 1. Inter-cell, intra-BSC handover. This is a typical handover scenario. The mobile station moves from one cell to another, but stays within the control of the same BSC. The BSC then performs a handover, assigns a new radio channel in the new cell, and releases the old one. Scenario 2. Inter-BSC, intra-MSC handover. As a BSC only controls a limited number of cells, GSM also has to perform handovers between cells controlled by different BSCs. This handover then has to be controlled by the Master of Science. Scenario 3. Inter-Master of Science handover. A handover could be required between two cells belonging to different MSCs. Now both MSCs perform the handover together. Scenario 4. To provide all the necessary information for a handover due to a weak link, MS and BTS both perform periodic measurements of the downlink and uplink quality respectively. Measurement reports are sent by the MS about every half second and contain the quality of the current link used for transmission, as well as the quality of certain channels in neighboring cells, the BCCHs. Receive level BTS, old receive level BTS, new MS measurement report MS BTS, old HO underscore margin M. MS BTS, new handover decision depending on receive level BTS, BSc, old measurement result master of science BSc BTS, new HO decision, HO, required HO, request resource allocation chapter activation, AC HO request, AC HO command, HO command, HO command, HO access, link establishment, HO complete clear command, clear complete. Clear complete intra-MSc handover. More sophisticated handover mechanisms are needed for seamless handovers between different systems. 19.